Okay guys, welcome back. Today we will see how to optimize our EDF we previously built. And okay, so most important things about this video is that you have to take the result as not as don't take the result as good, but just the effects of the modification you will add to your EDF and see the how to improve the performance. Okay, so let's think that this is your EDF that you build following the previous video I did, or you bought from Hobby King, and can be this is 6 blade, but can be 11, 12, whatever you want. Just pay attention to the effects that can have the modification we will see now. So first of all, we can see that the change in the momentum and also the thrust is generated by a difference between the inlet pressure and the outlet pressure. Okay, so considering that the change in the pressure that can be on the blade, we will have a thrust. So for increase the thrust in our custom built or recently bought EDF, we will reduce the area and increasing the speed, and also we increase the area. Okay, so just to take a quick look of the model, I had inlet lip and a reducer. Okay, this is our motor, but this doesn't take into account in increasing the performance. So what we're gonna do now is to take just a quick view of the flow simulation settings, and then we will go to the base case, and we will see the effects of the modification I will show you now. So this is base case. Okay, so general settings says that we have an external analysis type. We exclude the cavities, and also including internal space, because maybe sometimes you are not so also the pieces doesn't match very good. So excluding this internal space and cavities, the model is okay. Otherwise, maybe you will have some problems. I add rotation and a local region. Okay, so then we will go to the fluid. Okay, it's always air, laminar and turbulent, and the ambient condition are from default. Okay, so this is our EDF starting working at rest, at zero speed. If we were traveling, in this case we need to add the speed of our aircraft, but for this case we will start from zero. Okay, so let's do it in as a default. Then I add the rotating region. Okay, this rotating region is necessary because SolidWorks for flow simulation you cannot rotate the blades, but you need to build a cylinder that engulfs all the blades. Okay, so you can sorry. Okay, this is clear. Okay, you can see that the blades are inside our reference volume. So this is our rotating space. Okay, so I will hide it. I will take out this one. Okay, so let's go back. You can put both radian per second on RPM. I put 11,000 RPM, which is a 3S brushless motor running a 1000 kV using a 3S battery, which is 11 volts. So 11 times 1000 is okay, 11,000. Let's go to see our base case. Okay, so I will run it, I will mesh a new calculation, and I put 50 iterations only because it's just to understand the effects. Then if you want to have more details, you can increase the numbers, or you can add a local mesh and so on. But for our case, this is enough. Okay, mesh, run. This will take a little time, but it's no problem. Okay, yes. Lip. I didn't take into account the pitch of the blades, because it's a very difficult argument and cannot be explained in one single video. If you want to read, go and read the theory behind the pitch of a blade. Okay. Okay, now our solver is finished, and we will see the base case. Oh no, sorry, I did a big mistake. We have to disable all the parts. Okay, so we have the casing, the fan, and the brushless motor. So in this doing this, SolidWorks will consider only this part. So sorry, but we will run it again. It doesn't take a lot of time, but we can wait. Yeah, okay. So from component control, you can tell to SolidWorks what take into account when calculating. Okay, so in this case, we will run our base case, and then we will study the effects of the modification. These two lines are necessary for plot. Okay, so you need to add in whatever you want. It's not required to be a dedicated sketch, but you can add it here, or I don't know where is now. Oh, this one. You can see inlet and outlet. Okay, these are two lines, but just for reference. Okay, so now we will see the base case. Okay, we can see that SolidWorks takes into account the casing, the motor, and we can see the streamlines and the air, which is pulled out, and the blades and so on. Okay, so this is our base case. We will consider the modifications showing the x speed. Okay, this is the velocity in the z direction. Okay, which is this one. And why I take only z direction? Because from this formula, we see that the velocity is this one. Okay, so the change in the velocity is the change in the momentum and also the thrust. Okay, so we see that we have 0.250. Okay, so I will take 0.250. This is our base case. Then okay, so let's say that you bought a EDF that have another the inlet lip. So you want to add only, you can add only the reducer, the outlet reducer. So I will show you our outlet reducer, which is this one. It is custom made. I mean I didn't follow a specific rule. I just did it as I want. Okay, we have 68 millimeters in diameter, and we will reduce it up to we will reduce it on 60.8. okay, so 68, 7.2 millimeters in reducing. This is more or less 10%, a little bit more, but okay. So now we added, just this is a graphical representation. If you want to take into account, you have to go to component control and then tell to SolidWorks, oh, take into account this, the reducer. Okay, so just go ahead and let's see what happened. New calculation. Okay, this is base case. Calculating. Okay, this is the most common, because sometimes you buy an EDF that have some lip here and you cannot add nothing more. So but you can add a outlet reducer. Okay, so you can 3D print or what else. Okay, the solver has finished and we see the result. Okay, so now we can see that SolidWorks consider the lip, and we can, okay, and we see also that there is some difference between this graph and the other one. And okay, so now we have 0.64. okay, so 0.6400. %. Okay. Okay, so this is the 10% of the area was reduced. If you want to see the increase in the velocity, okay, I can show you what happens. Okay. Okay, we see that the maximum velocity is 5. Okay, but this is 5 meters. 5 meters per second. Max speed. Okay. Okay, so the distance, I mean, is I doesn't care where you measure. The fact is that you are measuring a difference. So if you want to draw the line here, we will have some effect. You will, if you want to draw the line here, another one, and so this is up to you. Now we will add the inlet lip. Okay, the inlet lip, I will enable to calculate also to SolidWorks. Okay, okay, the inlet lip is 77.6. okay, so 68, 77.6 minus 68. Okay, in this case is a little bit more than yeah, 60% or less. Yeah, or less, 50%. Okay, it's no problem. So okay, so now we will see what happens when you have fully modified your EDF. Let's go running mesh sub. Okay, oh no, sorry, oh no, I wrote that. Okay, perfect. And that's it. And then I will show you the effects only of the inlet, and then is okay. For you can increase some performance here, just making some streamlined or what else, but the contribution of this one is minimum. Okay, we are finished. We see, oh, what now, look what we have here. You can see that the performance is increased again. Okay, so what we will see is now what happened with the speed. Okay, we have two. Inlet plus outlet. Okay, and also if we want to see the speed, okay, okay, it's the speed. We have a 3.5, and also the both one we have 5 meters. So yes, okay, there is no big increase, but outside we have a higher speed increase. The last one, I will show you the effect of the inlet only, because maybe sometimes you have you can see that SolidWorks doesn't consider the outlet. Maybe sometimes you can only add the inlet. Okay, let's go see what happened. And now we see the inlet only. This is very simple, but the most important thing of this video is that you have to take into account the effects of the modification, not just the value. For example, in this case we have an increase in 200%. Okay, okay, you can see that here we have some turbulence behind, and also the pattern are not so good, but it's okay, and we will see what happens here. Okay, we have 0.8 meters second inlet only. Okay, so with this video the most important thing is to see the effects. Okay, we have 0.250 base case. If we just reduce the outlet on 10%, we have an increase in 2 times. Okay, yes, mostly. And then if we add the inlet and the outlet, we have almost 4 times. Okay, yes, more or less, just reducing for adding the outlet and the inlet. And if you cannot modify the outlet, just with the inlet only, no, we have 0.8, so we are almost 4 times, and this is 8 times. Okay, sorry. So the increase is very big, the enhancement is very high, and the amount of money and modification you need to do is very low. Okay, so this is all, and thanks for watching. See you on next time. Bye.